everyone, welcome to the course Fundamentals of Manufacturing Processes. So in today's lecture we'll be talking about metal casting. So I expect that the slides are visible and I'm audible. So this course is offered by Professor D.K. Dwivedi from Department of Mechanical and Industrial Engineering, IIT Roorkee, and I'm your TA Alka Jangir from IIT Kanpur. So firstly, we'll be going through some sample assignment questions which will be helping you in solving your weekly assignments. And then we'll be going through some lecture notes. So first question is, for steels, grain refinement can be achieved by alloying of. So steel has a lot of alloying elements. So which of these alloying elements would be beneficial for grain refinement? So if you know the answer, please type it in chat so that I know how much you already know and how much I have to tell further. Okay, so your options are carbon, vanadium, phosphorus and silicon. So type in chat if you know the answer. Someone has joined. Okay, so first question is, for steels, grain refinement can be achieved by alloying of. Your options are carbon, vanadium, phosphorus and silicon. So answer will be vanadium. So vanadium is one of the alloying elements which is used as grain refiner. Some of the other alloying elements and their roles are as given here. So in case of carbon, carbon is added mainly to increase the strength of the iron. So if you only have the pure iron, it has a very low strength. So by adding this carbon, its strength is improved. Second is manganese. So manganese provides, one has joined. Okay, so we are going through sample assignment questions for those who joined late. So carbon helps in improving strength. Manganese improves hardenability. By using that, it also improves toughness. And chromium is always used in stainless steels for improving corrosion resistance. Okay, someone else has joined. Chromium is used for improving corrosion resistance because chromium forms a chromium oxide layer. So this oxide layer is impervious and doesn't let any further oxidation. Someone else has joined. Okay, so for those who joined late, I am going through sample assignment question. So first question is, what is the alloying element that is used for grain refinement? So answer will be vanadium. So other than that, so carbon will be used for improving strength of the steel, and manganese will be used for increasing hardenability, and vanadium will be for improving strength by increasing the grain refinement. So grain refinement meaning its grain will be smaller in size, so it will be improving strength. So as I told earlier, by reducing the grain size, there will be Hall page type of equation that you read earlier, so that will be helpful here. And other elements, sulfur and phosphorus, acts as impurities in steel. Okay, and silicon acts as a deoxidizer. So for removing excess oxygen, silicon is used, and molybdenum is used for improving creep resistance, and it is used only up to 1%. And aluminum is used as grain refiner also. So out of these, if you had aluminum instead of vanadium, then aluminum would have been answer. And aluminium also forms oxides very easily, so it also acts as deoxidizer. And nickel acts as it is used for low temperature applications, because nickel is similar to manganese. It also increases hardenability of steel, and it also stabilizes austenite in steel. Copper is used for weathering steels, and titanium is used as grain refiner, and also is microalloying element. Next question is, the last step of the casting process of metal is. Your options are cleaning, finishing, inspection, injection of solidified metal. So if you know the answer, you can unmute yourself and tell the answer, or you can also type it in the chat. So try to answer this question, like what do you think is the last step in the casting process? So initial steps would be, firstly pattern making, then mold making, then you will be melting and pouring your metal, then ejection of your final product, then finishing and cleaning, then final it will be inspection. So inspection will be the answer. So this is the process. So first is pattern making, then molding, melting and pouring, ejection and cleaning, and heat treatment and inspection. So this is the, for die casting, it is the flow chart. So firstly your tools are made in which acts as mold. Okay, so then after that casting is pouring of your metal, and then after solidification it's cut off in small parts, and then grinding for the finishing. Then short blasting is also one of the processes of finishing, surface finishing, then heat treatment, and then finally inspection. Okay, so next question is, chills are placed in the mold. So if you have any query, you can unmute yourself and ask. Next question is, chills are placed in the mold. Your options are to increase the cooling rate of casting, or for venting the gas, or for alignment of mold boxes, or all of these. So which answer would be correct? You can type it in the chat box, or you can unmute yourself and tell what should be the answer. So chills in the molding, it is used to increase the cooling rate of casting. So for example, if you don't use chills, then the solidification may start from a place where it might become, you might have some defects such as misrun and other porosity. So chills are used for increasing cooling rate of casting. So first will be the answer. Okay, so these are the types of chills: internal chill and external chills. Okay, so for venting gas, this option is correct in case of vent wire. If it had asked what is the use of vent wire. So vent wire is used for making vent holes for the escaping of gases. And for alignment of mold boxes, there are pins and hole pair is given in mold boxes, and chills are used to increase the cooling rate. And in order to increase the local cooling rate of casting, the chilled material is placed inside the cavity, and the working surface is called chill. And the chills can be divided into two major categories: internal chills and external chills. Okay, so this one is internal chill. So it is kept internal to the mold. So this material of this chill should be similar to the what you are forming. Okay, so this metal, for example, if you are casting aluminum, then this will be solidified aluminum chips. So this will be cooling your material. The metal chill block that is placed in the cavity and can be melted into the casting is called internal chills, while the metal chill block placed on the surface of the pattern core box when core is called external chills. These chills won't come in contact with your final product, but it will be increasing the your cooling rate in these particular spaces. Next is the primary purpose of ingate in the mold is. So your options are for venting the gas, to ensure a mold cavity, to ensure mold cavity is filled by molten metal, or to feed the molten metal from runner to mold cavity, or to feed the molten metal when there is shrinkage of metal due to solidification. So which one should be the answer? You can type it in chat box. Okay, so answer will be to feed the molten metal from runner to the mold cavity. Okay, so primary purpose of ingate. Ingate is, in this particular figure you can see that ingate is these parts, these three. So firstly you have pouring basin in which you will be pouring your metal. Okay, and sprue is the guiding part to the molten metal from pouring basin to the choke. Choke will be where you are collecting your molten metal, and here some filtering also occurs. So if there is some heavy particles, that will go in choke, and then the molten metal will go through the runner, and after flowing through these it will go through ingates to the casting. Okay, and then after that there is riser. So after metal is appeared in the riser, you will be knowing that all the cavity has been filled. Okay, so the vent wire, so for venting is this part. So it is for vent wire is used for making small holes called vents through the sand mold to allow the exit of gases and steam during casting. If you don't use these vent holes, then what will occur? The gases that are coming along with the molten metal, or the gases that are forming because of the interaction between the your green sand and the molten metal, will make some steam or gases which get entrapped inside this your casting. So that will cause formation of porosity. So that's why formation of vents is required. Next is, in a casting, both runner and riser is used to pass the molten metal into the mold cavity. Okay, so from your runner your molten metal will enter, and from riser your molten metal will finally, after filling the casting, it will come out. The main difference is that the runner is a horizontal pathway. So as you can see here in the diagram as well, runner is always horizontal and the riser is vertical. And the ingates have the task of guiding the metal from the slack runner to the actual mold cavity. So in between your runner and your cavity will be ingates. Next question is, the liquid shrinkage during the solidification of metal casting is compensated by. Your options are pouring basin, risers, oversized pattern, or runner. So you can tell what should be the answer. So you can try to guess the answer based on what you have read throughout the week. Okay, so the answer will be risers. Okay, so liquid shrinkage during the solidification of metal is always compensated by riser, and the oversized pattern part is compensates the solid shrinkage. After solidification, whatever the shrinkage there is, it is by oversized pattern. Okay, so riser is provided to act as reservoir of the molten metal to compensate for the shrinkage of casting. Okay, so after this entire cavity has filled, the solidification will start from this side, and as it will keep on solidifying, there is density difference, okay, for the liquid and solid part. So there will be volume difference. So an extra material will come from riser. So the shrinkage and machining allowance is rectified by making pattern bigger than the required size of the final product. Runner and riser are used to pass the molten metal into the mold cavity, and excess metal then goes to the riser and gives an indication of filling of the cavity and provides metal to the cavity when there is shrinkage post solidification. Next question is related to your shrinkage. So whatever the allowance that you provide for the shrinkage, that is known as shrinkage allowance. So here you have aluminum blocks of 100 times 50 times 10 mm cube. So this is the volumetric dimension of your casting. These are to be cast by sand casting, and pattern allowance for aluminum is 13 mm per meter. Okay, so you have to take care of this unit very carefully. Okay, so for per 1 mm of the casting, you have to provide 13 mm increase in the pattern size. Okay, so this should be taken care of. And the dimensions of the pattern are, you are provided what should be the pattern allowance, and based on that you have to find out what are the dimension of the pattern. Okay, so 100 is the size, 100 mm is the size. Okay, so based on that you have to find out the pattern allowance. Okay, so answer will be the second one, and these are the calculations. So firstly, during cooling of the material in the casting process, the molten metal tries to shrink in size because of the increase in density, and the material is shrunk, reducing its dimension or volume. So the liquid shrinkage is compensated by providing a riser in the casting process, and solid shrinkage is compensated by giving a shrinkage allowance, which is expressed as mm per meter. Okay, so given that casting dimension is this 100, 50 and 10 mm, and the shrinkage allowance for the aluminum is 13 mm per meter, so it means that the shrink for the 10 it means that it will shrink by 10 mm if the size is 1 meter. Okay, so if your size of the casting is all around the volume is 1 meter by 1 meter by 1 meter, then in that case you have to add 10 mm in all those dimensions. Okay, but here your size is 100 mm, so you will have to multiply 100 to the 13 divided by 1000 to convert it into mm. Okay, so it will be 1.3 mm size you have to add as allowance. Okay, so it will be 101.3. So there are two options with 101.3. So you have to calculate two other options. So for the last one you can directly calculate, because in middle it is same. So for last it will be 10 multiplied by 13 divided by 1000. So it will be 0.13 mm. So you have to add this to the 10. Okay, so it will be 10.13. So this answer will be in between, second one. Okay. Next question is, material used for pattern making in casting is or are. So the pattern is replica of the final product that you want using casting. Okay, so it will be similar in shape to the casting, and it will be kept inside the sand mold, so for making the hollow cavity. Okay, it will be taken out before you pour your metal. So it can be made using metal, wood and plastic. All these are correct. Okay, so typically materials used for pattern making are wood, metal and plastics, and wax and plaster of Paris are also used, but only for specialized. Someone has joined. Okay, so your materials used for pattern making and casting can be metal, wood and plastic. Okay, so all of these. So it can be made of wax and plaster of Paris as well, but only for specialized application, for precise, because in case of wax you don't need to take it out before, so it can be kept inside, so it will give you more precise dimensions. And plaster of Paris is also used for more complicated shapes. Sugar pine wood is most commonly used material for patterns, primarily because it is soft, light and easy to work. Now wood can react with moisture in some cases, so in those cases you use metal and plastics, but metal and plastics are more expensive compared to wood, so wood is mainly used. Next is machining allowance. Your options are neutral allowance, positive allowance, negative allowance or zero allowance. So what does these mean? So in case of positive allowance, you have to make your pattern size bigger than the existing cavity and the final casting. And negative allowance meaning you have to make your pattern in lesser size compared to the casting. So in case of machining allowance, what happens, you have to machine your material to some extent for finding better surface finish. So for that you have to make your pattern always bigger than the initial size. Okay, so it will be a positive allowance. So machining allowance is provided to compensate for machining on casting, and the pattern is made slightly bigger in size, and the amount of allowance depends upon size and shape of casting, type of material, machining process to be used and degree of accuracy and surface finish required. So all these factors will influence how much of the extra material you will take, because in case of, as we saw in previous question, here you have almost precise dimensions that you will be taking, right? So here you already know that aluminum shrinks this much. Okay, after solidification it shrinks this much, so you have to take this much allowance. So in machining you have to base these things on type of material, shape of casting and machining process to be used and degree of accuracy and surface finish required. Next question is, if the permeability of sand mold is inadequate, then blank defects are found. So which defect do you think will occur? You can try to answer in chat box. Your options are surface crack, misrun, porosity and swell. So which one should be the correct answer? Okay, so answer will be porosity. Okay, so permeability basically helps in escaping of the gases that are trapped with the molten metal. So if the gases are trapped, then you will be having a lot of porosity. That will be your gases that will be trapped in form of porosity. Okay, so what are the other casting defects? those also I have tried to define here, so that if the question is other way around, so you can answer. So in case of misran is caused when the metal is unable to fill the mold cavity completely and thus leaves improperly filled cavities, and it occurs due to low pouring temperature and lack of fluidity. Okay, so here you can see this is the misran. So your metal is coming here, and because of this this type of structure, it's not flowing up to here, and also because of less fluidity of the metal can also be one of the reasons. And these are other. In case of swell what will happen, it is enlargement of mold cavity. So your basically if you have made sand mold, then some sand will get loose from the edges and it will lead to enlargement of your cavity because of the molten metal pressure, which results in localized and overall enlargement of the casting. So casting size will be bigger in case of this compared to pattern. Next is gas porosity, occurs when the metal traps gas, often nitrogen, oxygen and hydrogen during casting. So this is the how shrinkage cavity will look like. Because of shrinkage of this cavity, there will be this type of defect, and this is the porosity. So gases are trapped inside, and these are the hot tears, these are cold shots and cold shut. These are other defects which we'll study later. Do you have any query? If not, I'll go to the next question. Okay, so next question is the strength of moisture containing mold is termed as. Your options are dry strength, hot strength, green strength and cold strength. What will be the answer? Try to answer. So answer will be green strength. So moisture always depicts green. So if it is dry, then it will be will not be consisting any moisture after pouring of metal. Okay, so these are the definitions of these strengths for the sand. Okay, so firstly, green strength. So green strength is the ability of the sand to retain its strength, structure and shape while a mold is freshly made and full of moisture. So in case of sand casting, you can use different type of sands. Okay, so some sand will give you better green strength compared to other. So based on that you can decide which sand to go for. Next is dry strength. So dry strength is the strength of the mold after all moisture evaporates after molten metal is poured. So on the walls of the part where you have poured your material, so on that part your moisture will evaporate. So it will become dry in case, and the strength compared to that will be dry strength. So dry strength comes into picture when you are trying to remove your casting from the sand, from your mold. Next is hot strength. Hot strength is strength of the mold after mold gets heated up and is at the peak temperature. Okay, now these three definitions you should remember. Next is more shrinkage allowance is considered in pattern making for the casting of. Your metals are aluminum, lead, copper and gunmetal. So which one should be the answer? So answer would be the for one which shows highest shrinkage. Okay, so highest shrinkage is seen in case of lead. Okay, so during cooling of material in the casting process, the molten metal tries to shrink in size because of the increase in density, and in all three stages the material gets shrunk. reducing in the dimension or volume. But shrinkage allowance taking place in first two stages is called liquid shrinkage. Excuse me, someone has joined. Okay, we are going through some sample assignment questions for those who have joined late. Okay, so more shrinkage allowance is considered in pattern making for the casting of which out of these four metals: aluminum, lead, copper and gunmetal. So answer will be lead. So during cooling of material in the casting process, metal tries to shrink in size because of the increase in the density. Okay, because of solidification it will be having a crystalline structure, so because of that density will change. So in all the three stages the material gets shrunk, reducing its dimension and volume, but shrinkage allowance taking place in first two stages are liquid shrinkage, which is compensated by riser, and shrinkage in third stage is called solid shrinkage, which is compensated by shrinkage allowance. So liquid shrinkage is compensated by riser in the casting process, and solid shrinkage is compensated by giving shrinkage allowance. And shrinkage allowance is expressed as mm per minute, mm per meter. And the shrinkage values for different metals are given here. So in case of bismuth there is negligible shrinkage, and in case of white metal tin there is very less shrinkage, 5 mm per meter, and in cast iron 10 mm per meter. So what this unit suggests, so you have to take 10 mm size of extra in pattern compared to what will be the final casting size. So if your final casting size is 1 meter required, then you have to add 10 mm extra to the pattern. In aluminum it's 13 mm per meter, and brass 15, copper 17, steel 20, zinc 24 and lead highest here 26. So 26, with 26 lead will be the answer for this question. Now we'll go through some lecture notes. So for those who joined late, I'll repeat the questions once again briefly. Okay, so first question was, for steels, grain refinement can be achieved by alloying of. Your options were carbon, vanadium, phosphorus and silicon. So answer will be vanadium, because out of those carbon provides strength, phosphorus is an impurity and silicon provides deoxidizer, and vanadium is the only one which provides grain refinement. Aluminum can also provide grain refinement, but that's not the option here. Next question was, the last step of casting process of metal is. Your options are cleaning, finishing, inspection, ejection of solidified metal. So your answer will be inspection. Now this is the, yeah. Do you have any query? If not, then please mute yourself. If you have any query, you can ask. Okay, so last step will be inspection. So first step is pattern making, then molding, then melting and pouring, then ejection and cleaning. Then final, you provide heat treatment and you inspect it for any defects that are remain there. Next is, chills are placed in mold to increase the cooling rate of casting, for venting the gases, for alignment of mold boxes, or all of these. So answer will be to increase cooling rate. So there are two types of chills, internal chills and external chills. Internal will be similar to the casting metal. Okay, so it will be cooling your, it will be increasing your cooling rates. Next question is, the primary purpose of ingate in the mold is. Your options are for venting the gas, to ensure a mold cavity is filled by molten metal, and to feed the molten metal from runner to mold cavity, and to feed the molten metal when there is shrinkage of metal due to solidification. So last one is for riser, and out of other options, this one will be the answer, to feed the molten metal from runner to the mold cavity. So for these type of questions, you just have to remember this image, like how molten metal is flowing. So first it's going in pouring basin, then it's going through sprue, then choke, then runner, then ingots, then casting. So if you remember this image correctly, then finally riser. Then you can tell the answer of these questions. Okay, so ingot will be in between casting and the runner. So you can easily tell the answer, runner to the mold cavity. Next question is, liquid shrinkage during the solidification of metal casting is compensated by. Your options are pouring basin, risers, oversized pattern, or runner. So answer will be riser. So again you have to remember this image. Here, after liquid shrinkage, after this filling of this cavity, the molten metal appears in riser. So it also gives you indication of the filling of the cavity, and also it provides any material that is required for after shrinkage. So riser has multiple purpose. Next question is based on this shrinkage allowance. So you are given for aluminum 13 mm per meter is its allowance. So you have to for in terms of mm you have to calculate, and so for 100 it will be 100 times 13 upon 1000, and for 50 in terms of these you can add, and these will be added because it is a positive type of allowance. So all these things will be added to the existing size for the pattern. Next question is, material used for pattern making in casting is or are. Your options are metal, wood, plastic, or all of these. So answer will be all of these. So patterns can be made of all these things, but wood is widely used because it is cheaper compared to metal and plastic is cheaper compared to even metal. So, and wax and plaster of Paris are also used, but for specialized uses. Next question is, machining allowance is a neutral allowance, positive, negative, or zero allowance. Answer will be positive. So when you have to add extra material in case of pattern, then it is a positive type of allowance. So for machining, you will be removing some material from your casting. So for that you have to make your pattern bigger compared to the casting. So it is provided to compensate machining of the casting. Okay. Next question is, if the permeability of the sand mold is inadequate, then blank defects are formed. So permeability, if a sand has more permeability, then gases don't get trapped and they can escape easily. Okay, so in that case, if it is not good, permeability is very low, then gases will be trapped inside molten metal and will appear as porosity. Okay, so this is the porosity type of defect which will appear if your permeability is less for the sand. Next is, the strength of moisture containing mold is termed as your dry strength, hot strength, green strength, or cold strength. Answer will be green strength. So moisture and green, they are related. Okay, so you have to remember it in that sense. And after evaporating through molten metal, it will convert into dry strength. Okay, so these are the definitions that you can remember. Next is, more shrinkage allowance is considered in pattern making for the casting of aluminum, lead, copper, and gunmetal. So it will be for lead. For lead it is 26 mm per meter. Now we'll go through some lecture notes which will be helping you in solving your assignment questions. So firstly, steps of casting processes. So first, casting is one of the oldest forms of manufacturing. So the metal work, other manufacturing processes that you'll be studying such as machining, material removal and metal working and additive manufacturing, all those are relatively newer approaches compared to casting. Casting is the oldest one. And everything from artwork to engine parts can be created through this procedure. And in casting, molten metal is poured into a mold where it cools and solidifies. Okay, so this is kind of a definition that you have to remember. So the swords, armors of soldiers were often made by this manufacturing process, and casting is a traditional manufacturing process which involves pouring molten metal into pre-designed mold to create solid objects. And this method is fundamental in various industries and has been practiced for centuries. The mold is usually made of materials like sand, metal or ceramics. The molten material takes on the shape of the mold cavity and solidifies, and after cooling the mold is removed, revealing the final product. This approach allows the precise dimensions, intricate details and complex shapes, and finds extensive use in industries such as automotive, aerospace, construction, art and creating diverse and functional components. Now the definition. Casting process is a manufacturing method which involves pouring liquid metal, usually metal or plastic, into mold to solidify and form a desired shape for various industrial applications. So only metal and plastics. Why not ceramics? Because ceramics have a very high temperatures, melting temperatures, and so to hold that those at very high temperatures, you require refractories which can hold at very high temperatures, which is not an easy task. That's why ceramics are mainly made using powder metallurgy or some other routes. Metal casting is now a difficult, intricate process that indicates precise chemistry and perfect implementation. Despite the fact that modern technique may be comparatively new in the context of human civilization, the first metal castings date all the way back to around 4000 BC. And due to its malleability, gold was the first metal to be cast during that era. And due to the difficulties in getting pure ore, metal from tools and decorations were reused. So gold was the only one which doesn't form many different ores, right? Different oxides or different chlorides. So it was easier to melt and form it in form of a casting. Now these are the basic requirements of casting. Firstly, you have to form a pattern, then using pattern you have to form mold cavity, and then melting of this is the scraps that you are melting. Okay, so some scrap you already have available for in aluminum or other steels, you can melt those in furnace, then you will be pouring that material in mold. Okay, after pouring you provide some time for the solidification, and after solidifying of that casting you remove that from the mold. Okay, mold removal or ejection, and after that you clean the surface, and after cleaning and finishing can be using grinding and other processes, then finally you inspect your material for defects, and if it is okay then you take it further. Now we'll be going through all these processes in briefly. So firstly, pattern forming. So there are different types of patterns like solid or single piece patterns, two piece patterns, multi piece patterns, match plate patterns, gated patterns, skeleton patterns and sweep patterns. A pattern is a replica of the item that will be cast and is used in the casting process to prepare the cavity into which molten material will be poured. And the cavities in the molds are created using patterns which are typically made of wood, metal or model board. Okay, so after making a pattern, you also require core. So core is required. So in previous image, so this part is core. So if you want to form some casting which is hollow or where you can put something inside, then you require some core. So here in the core your material won't enter. Okay, so you can either make it as a solid, entire solid, and then machine it out, or to save some material you can use core as well. The process known as core forming involves the creation of the interior part of the casting, and the core prevents the metal from filling the complete space, while the mold gives the molten metal somewhere to go. Using cores, you can stretch mold projections to make more mold sections or to block out and make negative draughts. Now, mold making, and depending upon the application, a suitable mold is selected, and there are three types of molding processes. So expandable mold, permanent mold and composite mold casting. And then after that you will be melting and pouring your metal. Okay, so molten material, typically metal, is used in casting processes, and this molten material is then poured into a mold cavity that takes the form of finished part. And there are gates and runners designing in the core to facilitate the flow of liquid, and these gates and runners are essential because it is important that the molten metal flows very quickly, or else it would solidify before filling up the entire cavity. Now here you can better understand it first. So here you are pouring your metal from this side and it is filling the entire cavity, and then it is going through the riser. Okay, so after going through riser also provides some metal after some shrinkage. Okay, so there should be a particular direction in which it should solidify. If it solidifies from this side, then there won't be the extra metal can't come to the cavity, right? So there should be a particular direction of the solidification. So for that you can use chills as well, which we told earlier. Now once the molten metal fills the cavity completely, the process of solidification of the molten metal starts, and it is done by forced circulation to dissipate the heat energy, or by extracting the heat from the mold, or by natural convection. The entire casting process can be visualized in the animation that I have told earlier, and the cop and drag from the upper and lower casings for holding the mold of casting. So the cop and drag are divided at the parting line. So cop and drag are so upper part is okay, so this upper part, this is the parting line in between. Here it is shown better. So above part is cop and the lower part is drag. These are divided at the parting line. This is the parting line, this line, parting line, and the mold cavity formed by the pattern is enclosed by core in this case, and in this case there is sand. So the molten metal is poured through the pouring basin from where it reaches the gate, and the gate acts as a direction changer for the molten metal, and the small protrusion just after the gate is called as choke. So here this part where the molten metal is entering and changing its direction, This part is called choke. And this choke acts as a filtering agent to remove any contaminants present in the molten metal. And the molten metal flows in the mold through the runner. Runner is this horizontal part. So the molten metal goes through runner, and the air vent present just before the mold facilitates the removal of any air within the molten metal, and this helps in preventing the formation of air bubbles within and on the surface of the finished part. And the open riser acts as a gauge, and once the open riser is filled with the molten metal poured from the other side, we can conclude that the mold cavity is completely filled with metal. Now the mold can be left to solidification. So after pouring this, when you start seeing the molten metal through the riser part, then you can confirm that this entire cavity is filled. So you stop pouring further metal. Okay, now this is the ladle. This was previously kept in the furnace for melting of the scrap metal, and after that it is poured. Now for the solidification part, someone has joined. Okay, so solidification starts from the walls of the mold. Okay, so firstly it will start from the walls because those are the coldest part. So then it will move inwards, the solidification. So from here also you can see this is the cooling curve. So with time how your temperature will change. So in the liquid part you have provided some superheating. So after above the melting temperature you have provided some superheating so that it has good fluidity and it fills the intricate shapes. Okay, so after that it will start to solidify. This is for pure metals case. So it will solidify at a single temperature, and after that it will after solidification it will get cooled. So these are the various parts of the casting. So first is mold. So mold is the cavity of desired shape and size. So this is the cavity. Pattern was this replica, right? After that removal of the replica, you will be left with the cavity. So this cavity is known as mold, and it is always produced with due allowances for shrinkage of the solidifying material. And the latter types are generally made of metal or graphite. So, and due to high cost, their use is generally restricted to large production volumes. So these molds are either of sand or made of metal and graphite as well. For in case of metal and graphite, there is cooling rate is very high. Now these are some of the examples of mold cavities. Next is melting. So melting involves melting of metals and polymers, and then after that there is some melt treatment. Okay, so melt treatment, so after melting you can have presence of some oxides. So for that you need to provide some fluxing and degassing, alloying. These are other aspects. So in case of degassing, you remove any gases that might be left inside your molten metal, because at the higher temperatures your metal has higher solubility for the gases. So there is more gases, there are more likely to get trapped. So degassing is also required, and alloying. So for this you provide some alloying elements. So as I told earlier in one of the questions, okay, I'll go to the first slide. Okay, so these are the alloying elements. So these are for the steel. So these alloying elements you can add those after melting. Okay. So some of these are impurities such as sulfur and phosphorus. They are some impurities and others are added intentionally to improve the properties of the final product. Okay, so alloying, this can also be for grain refinement and some modifications as well. So after that, providing molten material with suitable furnace having proper temperature. Your furnace should have proper temperature, otherwise if it fluctuates more, then solidification can start inside furnace as well, which is not good for final casting. So proper temperature to have desired fluidity. So the higher the temperature you have above melting temperature, it will have higher fluidity and lower viscosity. And the time before solidification begins. Next is desired quantity. So for furnace also you select in a manner that you can have desired quantity as well. Acceptable quality and reasonable cost. Now this is one of the ladle. Ladle meaning which will be consisting your molten metal. So in this case you have liquid steel and this is the ladle bottom where you have helium purging. So it is a porous plug for helium injection. So helium you are adding for maintaining some two vacuum installation, and this is the ladle lid and there are ladle walls as well. Now to introduce the molten metal into the mold to produce a high quality casting that is fully tense and free of defects by allowing escape of all air or gases present in the cavity or those generated by mold metal reaction. So because in case of mold, if your mold is made of sand, then it will be having some moisture in it. Okay, so that moisture might react with hot metal and produce some steam. Next is minimum turbulence and time for feeding the metal, and next is minimum pickup of impurities from the atmospheric air. So now these pouring techniques can be different. So for example, you had this type of ladle. So if for the pouring, initially here also you had ladle, right? So pouring can be top pouring and it can be bottom pouring as well. So from bottom pouring, what you have certain advantages, right? So in some cases your slag will get collected at the top, right, because it is lighter in weight. So when you are pouring from bottom, that part won't be adding into your casting. So your casting will be sound compared to top pouring. So that is required in case of certain metals. Next is solidification process. Now it depends on the design of gating system and temperature gradient established after pouring of metal. Okay, so if how much temperature gradient is provided, so temperature gradient meaning what type of mold you are using. If you are using metal or graphite molds, then as I told earlier, the cooling rate will be very fast. So in that case your casting will be having more aqueous type of structure, and casting should be designed so as to have a directional solidification. So one which proceeds from one direction to another to avoid casting defects. So as I told earlier, the direction should be in such manner. So your riser part should solidify at the last so that any shrinkage can be compensated by the riser molten material. Okay, and shrinkage related to defects, porosity and crack under excessive restraint conditions and hot cracks are typical examples. Now these can be avoided if there is directional solidification. And these are the dendritic type of structures that you will study in further subjects. I think here we won't be studying about dendritic structure. And this is how your energy transfers occurs. So if this is, for example, if it is sand cast, then sand will be transferring your heat. Next step is mold removal. So after solidification, you will be removing your casting from the mold. So certain molds are single use molds, so they will be destroyed after that, after solidification, and certain are used multiple times. For example, your graphite and metal molds, they are used multiple times, while sand molds are destroyed. So casting is taken out of mold without any damage. So this step is also called ejection, and each of casting removal depends type of mold being used. So there are two types. With the ease of casting removal depends on type of mold being used. So it can be either single use mold or multiple use mold. In case of single use mold, these are destroyed after each casting, and so no serious difficulty in removal of these casting. Multiple use molds, so you have to take care that your mold doesn't damage as well and your casting also doesn't damage. So it is more complicated. So the removal of complex shape casting impose major mold design problem. Next step is cleaning, finishing and inspection of casting. Okay, so firstly, initially you sew, right? This is how your mold cavity is formed. So this riser part and pouring basin part, these are also will be having solid metal which will be attached to this part, this your casting. So you have to remove these as well by cutting off, by machine removal. Okay, so extra material which is here, it's shown here as well. This part is your riser part. Okay, so this also have to be removed. So the extra material remains attached with the casting in form of metal solidified, and at gate and the riser, this gate and riser, these have to be cut off along the mold parting lines. So parting lines will also, there will be some lines also formed on these which also need to be grinded. Next is mold material adhered to the casting surface. Okay, so from mold, so if you used sand mold, then some sand will also get adhered to the molten metal. Okay, after solidification it will be attached to the metal, the sand. So that also you have to remove. So all these materials should be removed from the finished casting. Okay, so this castings are inspected for defects. So this removal can be through grinding or polishing and sand blasting. All these processes are used, and then after that your casting is inspected whether it has some porosity left, which either it leaves it usable or not. Next is casting terminology. So firstly you have this part. So I have told you about the most of the terminologies. So pouring cup, where your material will enter first, then through sprue it will go, then this is the choke where it will change its direction, then this is the runner, this is the riser part, then you have this is the closed riser. Sometimes you have open riser as well. So as I told earlier, in here you have a open riser. If it is formed inside the casting, only inside casting, then it is a closed type of riser. Okay, then you have mold cavity. core to make your shapes hollow, and core print for holding this core, it is core print. Drag is the part of the flask which is lower part. Corp will be upper part. Next you have parting line where your corp and drag is matching. This is the parting line. Okay, then these are the your core box and casting, all these are shown. Now we'll go through the definitions of various of these terminologies, right? So first, cores. So cores are used to create complex shapes and hollow sections in the mold. Okay, so then next is gating system. So channels and gates, they control molten material flow. Then risers, it is additional cavities compensated for shrinkage during solidification. So as I told earlier, you have two types of risers, open and closed risers. Then you have venting system, it allows air and gases to escape from the mold cavity. Molding flasks, so this is the rigid frames that support the mold during casting. So molding flask is of it is made of cope and drag. Then you have molding tools which are used for packing, shaping and smoothing of the mold. Then you have pouring equipments, transferring of molten material into the mold. So ladle, furnace, all these will count in pouring equipments. Cooling and heating elements, so it controls the solidification and maintains the temperature. Now pattern is the replica or model of the final casting. So it will look exactly like what your final casting will be, but it will be different in the material. So for example, if you have to make some aluminum block, then you can have your pattern to be of wood or different metal as well, but it will be having some allowance given to it. So it can be little bit bigger or smaller in size to the exact casting. Then molding material is packed around the pattern and pattern is removed to produce the mold cavity. So mold will be your cavity part, right? So molding material can be sand, it can be of different other things as well. Next is flask. So the mold containing the molding aggregate. Okay, so flask is this part, right? So this part is made of metal, mainly made of metal or steels. So in this part you can fill sand, so it will retain this shape of this sand. Next you have cope. So in flask you have top half of the pattern, so it is flask mold or core in the two-part mold. So this is two parts, so upper part will be cope and the lower part will be drag, right? So this is your core, and here you have parting plane, runner and gates, sprue, basin, all these things. Next you have drag, which refers to the bottom half of the pattern, flask, mold or core in a two-part mold. Next you have core, it is a part that is inserted into the mold to produce the internal structure of a casting, such as holes or passages for the water cooling. Next you have core print. So it is region added to the pattern, core or mold, which is used to locate and support the core within the mold. Next you have mold cavity. So after removal of pattern, you will be left with the mold cavity. So the cavity, which is formed by the combination of the mold material and core, into which the melt is poured and solidified to produce the desired casting. Next you have riser. Riser is a reservoir of the metal that can compensate for any shrinkage that occurs during solidification. So here again you have a different types of casting. Next you have gating system, which is a network of channels used to deliver the melt to the mold cavity. Next you have pouring basin. It is a portion of the gating system that initially receives the melt from the pouring vessel and controls its delivery to the rest of the mold. Next you have sprue. So sprue is the vertical portion of the gating system through the melt which travels down from the pouring basin. Next you have runners, which is horizontal channels of the gating system. So runner is this horizontal part. Sprue is where you are pouring. After pouring cup you have in between sprue. Horizontal channels of gating system through which melt enters into the mold cavity. Then you have gates, which has controlled entrances of the gating system into the mold cavity. Gates are the in gates that I told earlier. So in between your cavity and your runner you will be having gates. Then vents. So vents are this gas vent that is shown here for escaping of the gases. So additional channels included to provide an escape for the gases generated within the mold. Next you have parting line. So it is the interface which separates the cope and drag halves of a mold, flask or pattern, and also the halves of a core in some core making processes. So your core can also be in halves. Then the line which is separating this cope and drag, this will be parting line. Next you have draft. So it is taper on a pattern or casting that permits its easy withdrawal from the mold. So draft will be if you make your, for example, you taper your pattern, then it will be draft, taper of the pattern. Now these are various tools which are of use. So vent rod I told earlier for making vent holes in your sand. Next you have wire mesh this is for sand. Sleek, sprue, bellows and molding box. Rammers also you use for sand, for settling of sand in case in flask. Next you have again all those terminologies in short form. So flask is a framework made of metal or wood which serves as a container for creating molds. Cope is the upper section of the flask, which also known as cope. Drag is the lower section of the flask, known as drag. Core is the component used to create an internal hollow space within the final product. Vents is opening intentionally created in the mold to allow gases produced when the molten metal interacts with the sand to escape. Mold cavity is the empty space within the mold where the metal part is formed. Riser is the reservoir of molten metal which provides additional material to compensate for any shrinkage. Runner is a passageway through which the flow of molten metal can be controlled before reaching the mold cavity. Pouring cup is a container or basin used for pouring molten metal into the mold. Pattern is a replica of the required shape used in the molding process. Sprue is a channel through which molten metal flows downward. Parting line is the boundary that separates the cope and rake sections of the mold. Now next 13 and 14 chapters are related to pattern allowances. So the types of pattern allowances: shrinkage allowance, draft allowance, machining, distortion and shake allowance. Firstly, shrinkage allowance. So it is provided to compensate for shrinkage of material, and the pattern is made slightly bigger compared to your final casting, and the amount of allowance depends upon type of material, its composition, pouring temperature and etc. Okay, I am going through lecture notes for those who have joined late. So in case of shrinkage allowance, you provide extra material in case of pattern to compensate for shrinkage of material, and the pattern is made slightly bigger, and your amount of allowance depends upon type of material. So final material that you are casting, for example aluminum, lead, for all those I told what will be the amount of allowance required. For lead it will be higher compared to bismuth and other materials. And its composition, so it will depend on composition of the final product. It will depend on pouring temperature, so what temperature you are pouring, so from that part to solidification temperature it will vary its density. That's why you need to decide allowance based on that. Now during cooling of material in the casting process of the molten metal, it tries to shrink in size because of the increase in density in all three stages. The material is getting shrunk, it's reducing its volume. But shrinkage allowance taking place in first two stages is called liquid shrinkage, and shrinkage in third stage is called solid shrinkage. So the liquid shrinkage is compensated by the presence of riser in casting, while solid shrinkage is compensated by giving shrinkage allowance, and it is expressed as mm per meter, and the shrinkage values for different metals are given here. So for bismuth it was negligible, for white metal 5, cast iron 10, for aluminum 13, brass 15, copper 17, steel 20, zinc 24 and lead 26. Next you have machining allowance. So it is provided to compensate for machining on casting. So always when you cast some material, so it will have it won't necessarily have good surface finish. For example, in case of sand casting, you have very poor surface finish compared to die casting and other castings. So that's why you need to give some machining allowance in case of sand casting. So for machining, what you do, you will be machining some of the material from the surface. So that material should be counted in case of making pattern. So your pattern will be made slightly bigger than the exact size that you require for the final product after machining. Okay, so the amount of allowance depends upon size and shape of casting. So and also it depends on type of material. So some materials require more machining for surface smoothing. So based on that, and machining process to be used, so what machining process that you are using for smoothing, and degree of accuracy that is required, and what is surface finish that is required. Based on those you decide. It won't be an accurate compared to your shrinkage allowance. In that case you know exactly 5 mm per meter how much allowance you already require. But here it depends on various factors. Next you have draft allowance. So for example, if you have a final casting that is in this square form, right? So if you are removing this pattern from this mold, then it will leave some tears in this sand. So now these tears will act as it will reduce the strength of this mold, right? So if then you'll be pouring your metal, then it will be giving you some shape which won't be as accurate as the initial one, as the pattern one. So for that you choose a shape which is tapered. Now in case of tapered, when you remove this casting, it is very easy to remove. Okay, so in ice cream as well, you sometimes see your ice creams are tapered, so these are for easier removal of them from the mold. Okay, so that same concept is followed here as well. Okay, so similar concept is followed here as well, because in this case with the little force you can get away with the walls, but in this case your walls will be in contact for the entire range. So that's why there will be more tear in case of your this type of shape. So tapered casting is preferred. So after casting this, you require some this cuboid type of shape, then you will be machining. One second, let me use pointer. So you'll be cutting off this much part from this part for getting your cuboid shape, final cuboid shape. Okay, so draft is required in that case when you have chances of this tear in case of sand. Next you have distortion allowance. So it is provided on pattern whose castings tend to distort on cooling. So there may be certain metals which show this type of distortion, and so it will occur in case of when your castings are of U, V, T, L shapes, then there is some distortion allowance that should be given in opposite sides. Next is shake allowance. Okay, so when you take out your pattern from the mold, so what happens? So your sand will be attached to the pattern, right? So after, for removing this, you need to shake your pattern to get it out. So for this shake, your mold cavity becomes bigger compared to your pattern size. Now your casting will also be bigger compared to pattern. So now you have to count this as well. So this is a negative type of allowance. So to facilitate the enlargement of the mold that takes place during the removal of the pattern, and the pattern shakes during the withdrawal from the mold, resulting into larger size mold cavity compared to your pattern. So that's why this is a negative type of allowance. Chapter 15, you have sand molding. So sand molding will be where you will be using, your mold will be made using sand. Okay, so first is mold characteristics. So these are various characteristics of mold. First is permeability. So permeability will depend on the sand. So and permeability of soil depends on the average size of the pores, and it's related to the distribution of particle sizes, particle shapes and soil structure. So your sand particles, whatever its size and its distribution, that all will decide what is the gap between them. So permeability meaning what is the porosity between them. So it can allow some gases to escape. So permeability comes into picture when you see what will be the final porosity in your mold, right? So if it is not nicely permeable sand, then the gases will get entrapped and they will act as porosity in your casting. Next characteristic is strength. So strength of sand, it can be of different types. As I told earlier, it can be green strength, hot strength and dry strength. and these are the definitions. In case of green strength, it is the ability of sand to retain its strength, structure and shape while a mold is freshly made and full of moisture. Dry strength is the strength of the mold after all moisture evaporates after molten metal is poured into the green mold. Hot strength is the strength of the mold after mold gets heated up and is at peak temperature. Next characteristic is refractoriness. It is the ability of the molding sand mixture to withstand the heat of the melt without showing any signs of softening or fusion. So it should withstand high temperatures. If your metal you're choosing for casting has very high melting temperature, then depending on that you choose your sand. Next is collapsibility. So after you have solidified your casting, then during ejection of your casting, then you require collapsibility in sand. So if it collapses easily, then your casting will be taken out easily without any damage. So the ability of molding sand to collapse after solidification of the molten metal, it is collapsibility. And after the solidification of molten metal, the sand should get collapsed for free contraction of the metal. Next is the types of sands. So these are the 5 types of sands. First is green sand. So it is the sand or sandstone which has a greenish color. It is a mixture of silica sand with 18 to 30% clay having total water of 6 to 8%, and it is soft, light and porous with clay and water furnish the bond for the green sand. Next you have dry sand. It is the green sand that has been dried or baked after the mold is made and is called dry sand. Dry sand is suitable for large castings, and the molds prepared in dry sand are known as dry sand molds. And if we talk about the physical composition of dry sand, it is similar to green sand except for water. So only the moisture has vaporized. It has evaporated after it comes in contact with the hot metal. So facing sand, it forms the face of the mold. Okay, so when you will be putting your pattern, then between pattern and your sand you will be putting facing sand. So the facing sand is used directly next to the pattern surface and comes into direct contact with the molten metal when the molten metal is poured into the mold, and it has high strength and refractivity as it comes in contact with the molten metal, and it is made of clay and silica sand in addition to unused sand. Next is backing sand. The backing sand is also called floor sand, used to back up the facing sand, and it is an old and frequently used molding sand which is used for backing purposes. It is sometimes called black sand because of the addition of coal dust and burning due to the contact with the molten metal. Next is parting sand. Parting sand will be having very coarse particles. So for the partition of your cope and drag, you require to put some parting sand so it comes off easily, and in between pattern also you put some parting sands for easier removal. The parting sand is used to avoid sticking of green sand to the pattern, and it also allows in the easy removal of cope and drag. This parting sand serves the same purpose as dust, and it is pure clay free of silica sand. So I think there is Okay, so in between this pattern and this mold, in between this you will be putting parting sand for easier removal, and it will be having coarser particles compared to your sand that you are using in between the green sand. Okay, next is factors that affects the fluidity. So why fluidity is required? So fluidity is required in case you want to make some intricate shapes or good filling of your mold cavity to each and every final complex shapes. So if your material has good fluidity, then you can form complex shapes very easily. So the metal being used, your this factor will be affecting. So whichever metal that you are using, its solidification temperature range. For example, if you are using copper nickel type of copper nickel alloy, so at what composition you are using, based on that it will have solidification range. Okay, so solidification temperature range will change with the composition. So if this range is very high, then fluidity will reduce. So this range should be lower. And surface tension of your material, viscosity should be lower. So as you go above the melting temperature, your fluidity increases. Heat content, superheat, so it is again the temperature above the melting temperature. So with that your fluidity increases. Next is mold. So these are the characteristics which are related to mold. So thermal properties. So what is the for example, if you are using sand mold or you are using graphite or metal mold, that will also define the fluidity. If you have a mold that has very high thermal conductivity, then it will get solidified very fast at the walls. Okay, so your material should be insulating if you want have higher fluidity. Next is permeability. So permeability of sand will also define the fluidity. And surface roughness of the mold wall. So surface finishing will also define the fluidity. Next is conditions of poured metal. So the temperature of pouring. So at what temperature you are pouring your material above the melting temperature, that will also decide the fluidity. Next is types of casting. So first type is sand casting process. So here in animation you can see this is the pattern, this is the sprue and riser, and this is you are filling the sand, and then using rammer you are giving it a shape. Okay, then you will be separating this scope from drag, and you will be removing the pattern, this sprue and this riser, these wooden shapes, right? Then there will be cavity left behind. So in that cavity you will be pouring your molten metal, and then it will be solidifying inside this sand, and after solidification you will be again separating these boxes, and then you will be taking out your final casting. Okay, so in the industrial process known as sand casting, liquid metal is poured into a sand mold that has hollow cavity in it and is then left to solidify, and a liquid substance is poured into a mold during casting, and the solidified material takes on the intended shape. So this is basically mostly used for non-ferrous alloys. So non-ferrous alloy casts are frequently made through the process of sand casting, and this procedure was created over 6,000 years ago but is still being updated. There are three types of sand used in casting: green sand, water glass or sodium silicate, and resin sand. Next you have die casting process. So in previous case you had to create this entire hollow shape, right? In this case you will be having this hollow shape made using CNC. This die will be filled with material, and here you have parts which are metallic, so heat transfer will be very fast. Die casting is process which involves melting metals and injecting them into already made mold, and the metals used in die casting have low melting points. Mold or tools that are made of steels that has been specifically manufactured for a given job using manufacturing techniques like CNC machining. Okay, and die casting sheet metal components have high level of accuracy, precision and repeatability as a result. And two die casting processes used industrially are hot chamber and cold chamber die casting. Okay, so why precision is high? Because in the die that you are using, it will be same. So if you are filling metal again and again, so it will be giving you same type of structure with same type of defects. But in this case, each time you are making this mold using sand, so because of the human error you will be having different types of casting, so it won't be as repeatable. And in this case you will be having metals which are having low temperature, because you are limited with the steel that you are using, right? Steel you can use to particular temperature compared to your sand. Sand is a ceramic type of structure, right? Silica. So that's why you can use it up to higher temperatures compared to die casting. When dealing with materials with low melting points such as zinc, tin, lead and magnesium alloys, the hot chamber die casting process is ideal, and it is inappropriate for alloys with higher melting points because doing so would harm the pump, because the metal would come into direct contact with it, and it entails using pressure from a hydraulic system to pour the metal into the die after it has been melted. Working with materials that have a high melting point such as aluminum demands cold chamber die casting technique. Since the high melting temperature required for such metals can harm the pumping system, this method is perfect for them. So this is how you will be pouring your metal, and this will be filling inside die and then ejected from this. Next is pressure die casting. So in previous one you had only die casting, here you will be applying some pressure as well. So this pressure will be helping you in getting very intricate shapes. Pressure die casting is a quick, dependable and economical manufacturing process for the production of large volumes of near net shaped, precisely tolerated metal components. And in general, the pressure die casting method involves injecting a molten metal alloy under high pressure into a steel mold or tool, and this quickly solidifies between a few milliseconds and a few seconds to create a component with net shaped component, and it is then automatically extracted. There are two kinds of pressure die casting: high pressure die casting and low pressure die casting, depending on the pressure applied. So in previous it was separated based on temperature. So temperature here, okay, so okay. Next, hot chamber and cold chamber dies, right? Here it is separated based on pressure. So low pressure and high pressure. So high pressure die casting and low pressure die casting depending on pressure that is applied. While nearly 50% of all light alloy casting production is done using high pressure die casting, it has a broader range of application, and about 20% of overall production is currently made using low pressure die casting, but this percentage is rising. And for casting needing a precise tolerance, the intricate geometry, high pressure castings are essential. Because of the additional pressure, the metal can be forced into more intricate feature. And for larger, less important components, low pressure die casting is frequently used. So for intricate shapes, you will be requiring high pressure. Next is shell mold casting. Okay, so in this case you will be first having a pattern, and based on that pattern you will be sticking some sand on it, sand with resin binder. So this sand is binded on this, and then this binded sand is removed from this, okay, this shell. After heating, you will be heating it in a chamber, then remove it, and then these type of this sand from these molds that are made from sand, these will be acting as a mold, right? So in this case, molten metal is poured into a disposable sand based mold during the metal casting procedure known as shell mold casting. It is similar to sand casting, but when using a shell mold casting technique, sand resin mixture is applied around a pattern to make a thin walled shell as the mold, and the pattern, a piece of metal in the form of the intended part, is used repeatedly to create shell molds. And the higher production rates are possible with reusable patterns, and complicated geometries can be cast using disposable molds. This method is more productive, has better dimensional accuracy, and requires less labor than sand casting, and it is frequently employed for tiny to medium sized parts that demand extreme precision. So for more precision you go for shell mold casting. Next you have investment casting process. So in this case what you will be having, you will be having a gating system, entire gating system, and these all final patterns in form of wax, right? Now this wax will be dipped inside ceramic slurry. Now this slurry will keep on forming walls on this. So you will be doing this multiple times and forming some ceramic walls. Then this wax will be evaporated, and in this hollow ceramic shell you will be pouring molten metal, and then you will be removing this from this ceramic shell. Okay, now in this case investment casting, a wax pattern is coated with a refractory material to make a mold, which is then heated away before pouring molten metal into the cavity to solidify. And the investment casting, also referred to as lost wax casting, is a precision metal casting process that, when compared to other manufacturing processes like sand casting, which produces castings that are highly accurate and meticulously detailed. A wax or appropriate polymer pattern is coated in investment casting by being dipped into slurry of refractory material, and this dipping procedure is done several times to increase the coating thickness and strength after the refractory material coating has hardened, and the wax is melted and molten metal is then poured into the cavity produced by the wax pattern after the final coating has solidified. The refractory mold must be broken in order to extract the metal casting after it has solidified inside the mold. Okay, now after this you have centrifugal casting. So in this case you will be using centrifugal force, right? So this molten metal is poured, then you will be rotating this part. So this helps in getting defects reduced. Centrifugal casting is a casting procedure which uses centrifugal force to produce cylindrical shaped castings, and this technique is ideal for creating hollow components with exceptional integrity and controlled grain structure. So it also influences grain structure. Someone wants to join. Okay, so we are going through lecture notes. So next is centrifugal casting. These castings are not defined in lecture notes, but you need to know briefly what these are about. Centrifugal casting, typically the centrifugal casting process is employed in the production of pipes, cylinders and other tubular parts. So these will be hollow in shapes. The process of creating a casting involves pouring molten metal into a mold or die that rotates either horizontally or vertically, and the desired shape and size of the casting determines the orientation of the mold. As the mold rotates, centrifugal force causes the molten metal to move towards the inner surface of the mold, resulting in a hollow cavity with uniform thickness. Next, you have advantages of casting processes. So casting is very old process, right? So it is being used for around thousands of years. So there are several advantages of casting over other manufacturing processes. Someone has raised hands. Do you have any query? Okay, if not, I'll continue. You can ask. If you have any query, you can unmute yourself and ask. Okay, so there are several advantages of casting process. So you'll be getting smooth finish in die casting and other castings. You'll be getting very smooth finish. In sand casting, you'll be requiring some finishing, yet you find some smooth finish. Next, you have faster production, and you have high tolerances, and you have affordable tooling. So the tools that I showed earlier for the casting, those all are very affordable compared to other processes such as rolling, extrusion and all. The casting procedure uses affordable tools and machinery. Vast size range, so the casting can be created in any size and form, and up to 200 tons any dimension casting can be done. So very tiny parts to the around 200 tons also you can cast easily. And material variety, we can cast any type of material, so plastics, metals, alloys, some composites as well you can cast easily. Composites are casted using stir casting and some other castings. Next, you have, it is possible to create intricate and complex shapes, and it is the most affordable method to produce various shapes, sizes and mechanical characteristics. So by controlling the cooling rate, you can control the microstructure as well. So that's why you can get different types of mechanical characteristics. There are some disadvantages of casting as well. So first is, it is high possibility of faults, and in some circumstances it is impossible to fix flaws. So if you got porosity, for example, or some hot tears in your casting, so if it is inside your casting, then it is very hard to get rid of. If it's on surface, then you can remove it and if you count it in machining allowance, then you can easily remove it. And casting does not produce very accurate dimensions as compared to precision machining process. So machining process is a secondary process. For that you initially need some material which has been casted or which has been made through powder metallurgy. So this is also one of the advantage of casting, that it is a primary process. Okay, now casting won't be giving you final accurate dimension which you can directly use as a machine component. So to make it in form of, for example, thread or a bolt, you need to give it some accuracy or precision through machining. Next you have sand casting, which is a common casting method, typically requires a lot of labor. So sand casting process I told, so it requires a lot of labor. Now these are the applications of casting processes. So first is industries use the casting method to produce a variety of goods including hollow cylindrical shapes, automotive pistons, pulleys, engine manifolds, valves, nuts and defense equipments. The casting process is used in many different sectors, including those related to aerospace, defense, automobiles, railroads, construction, agriculture, mining and chemicals, and in the creation of ornaments and house decor it is also employed. Cast steel is used to produce a significant amount of continuous forging. Copper, aluminum, silver cast irons, white cast irons, aluminum bronzes, oxygen-free copper and other metals are also continuously cast. And for rolling, extruding or forging purposes, metals are cast as ingots. So for these processes you require initial material which is made through casting, and these are in form of ingots and also sometimes in long shapes with basic cross section which are cast as round, square, hexagonal rods, etc. Okay, so that's the end of the presentation. I'll leave on the screen these question answer for those who have joined late. So these sample assignment questions might help you in solving your assignment of this week. Okay, so first question was related to grain refinement. So you can take a screenshot for those who have joined late, and if you want to take screenshot. Otherwise PPT will also be available for you. Next question is, last step of casting process of metal is? Answer will be inspection. Next question is related to chills. So in this case, chills are placed in the mold. So these can be internal, these can be external chills. These are to increase the cooling rate of casting. Next question, you have primary purpose of ingate in the mold. So answer will be to feed the molten metal from runner to mold cavity. Okay. Next question is, liquid shrinkage during the solidification of metal casting is compensated by. Answer will be provided by risers. Oversized pattern will be for the solid shrinkage. It won't be in case of liquid shrinkage. Next is, you have to find out the dimension of pattern. So final block should be of these dimensions. So you have to add certain part for the so for adding you are given 13 mm per meter is the pattern allowance, right? So you have to for 100 mm you have to multiply with 13 divided by 1000 because it is per meter. So for 13 you will be divided by 1000. So it will be adding will be 1.3 mm. For 50 you have to add 0.65 and for 10 you have to add 0.13 mm. Next question is, material used for pattern making in casting is or are. Your answer will be all of these. So metal, wood, plastic, wax, plaster of Paris, sugar pine wood, all these are used as pattern material. Next is, machining allowance is a positive allowance. So when you have to add extra material to your pattern, then it will be a positive type of allowance. So machining allowance will be positive and shrinkage allowance, that will also be positive, and the allowance which is negative is a shake allowance. So it is provided to compensate for machining on casting. Next question is, if the permeability of sand mold is inadequate, then blank defects are formed. So answer will be porosity. So permeability is how easily your gases can escape from the sand. So if it is not adequate, then it will get trapped and it will act as porosity in your material. Your gases get trapped. Okay, so porosity will be the answer. Next question is, the strength of moisture containing mold is termed as. So answer, moisture related answer will be green. So in case of moisture, so once having moisture will be green strength. After it has come in contact with molten metal, it will be dry strength. When it is at peak temperature, then it will be hot strength. Final question was, most shrinkage allowance is considered in pattern making for the casting of. Your options are aluminum, lead, copper and gunmetal. So out of these, shrinkage allowance is highest in case of lead. So lead has 26 mm per meter. So this much shrinkage allowance you have to provide. Okay, next up we went through the lectures. First lecture was steps of casting processes. Then we went through the casting terminologies. 12th lecture. Then we went through pattern allowance, lecture 13 and 14. And then we went through Okay, this was shake allowance. This is the negative one. Next we went through sand molding. So sand molding will be continued in next lecture. Okay, so if you have any query you can ask. Okay, if not, I'll be ending the class here. Yeah, do you have any query? Okay, then I'll be ending the class here. Thanks for joining.